This is Lecture 4 of the Quantum Formalism Differential Equations Review Lectures. Today we'll discuss complex and repeated roots of the characteristic equation. So to start with, we'll look at complex roots. A little recap from the previous lecture. We saw how to solve second-order linear homogeneous differential equations with constant coefficients in some cases, namely when the real roots were distinct. And how we did that is we used the superposition principle and this notion of the Wronskian determinant to figure out that if we had two solutions, then any linear combination of those would be a solution. And if the Wronskian determinant of those two solutions was non-zero, then a superposition like that could solve every initial value problem for an appropriate choice of constants. We also use this characteristic equation to figure out that this exponential function y is equal to e to the rt will be a solution to this differential equation if and only if r is a root of the characteristic equation. Okay, so if you have complex roots and you don't mind complex valued solutions, for example, in quantum mechanics, that's usually the case, then we're fine. We can do pretty much exactly the same thing as in the real distinct roots case, as long as they're distinct. Yeah. So if the differential equation has real coefficients, then complex roots will always be distinct. But if you had a differential equation with complex coefficients, it could be possible that the complex roots are repeated, and then things wouldn't be quite so simple, but we'll talk about repeated roots towards the end of this lecture. Okay, but anyway, yes. If you had distinct complex roots, then y equals c1 e to the r1t plus c2 e to the r2t will just be the general solution with c1 and c2 arbitrary complex solutions, arbitrary complex numbers. If you don't know what this exponential function means, when you're allowed to plug in complex numbers, we'll talk about that in just a little bit. But there is a way to make sense of this, right? This isn't a notion of sort of multiplying this real number e some complex number of times. There's a way to make sense of that formally, which we'll see in just a bit. Okay, but what about if we're interested in real valued solutions? Say we have a differential equation with real coefficients, and we're only interested in real valued solutions. For example, this classical mechanics problem, if you have a mass on a spring with friction, that's a very good example of a differential equation like this, with a second-order linear homogeneous differential equation with constant coefficients is exactly this setup. M is the mass, gamma is some coefficient of friction, and k is a constant coming from Hooke's law. All right. So in this case, the position of this mass on a spring is definitely supposed to be a real number. It shouldn't be a complex number. So we really do want a real valued solution to this differential equation if we're interested in a physical capacity. And if there's not too much friction, so if this gamma squared is less than 4km, then you will have complex roots. And it is the case that if the differential equation has real coefficients to start with, then your complex roots will always be a complex conjugate pair. This is just coming from the quadratic formula. If you look at the quadratic formula, if a, b, and c are all real numbers there, then you're going to end up with a complex conjugate pair like this, if the roots are complex. Okay, so in the zero friction case, gamma is equal to 0. It's not too hard to actually guess what two solutions are to this differential equation. So maybe even like the simplest case would be something like y double prime plus y equals 0. Or in other words, y double prime is equal to negative y. So for something like that, you just think, are there any functions with this property that when you take a second derivative, you end up with minus the function you started with? And yes, sine and cosine both have those properties. And so if instead you're looking at my double prime plus ky equals 0, it's pretty similar. Then you have y double prime should be minus k over m times y. And then you can see sine and cosine will work as long as you put this square root of k over m inside the function, so that when you take a derivative, the square root of k over m pops out, and then when you take another derivative, you'll get k over m in total. Okay. So yeah, so this is how it works if gamma is equal to 0, but what if that's not the case? What if you have a non-zero value of gamma, or maybe you were just looking at a second order linear homogeneous differential equation with constant real coefficients, and you ended up with a complex conjugate pair of roots like this? What can you do? Well, you can end up doing something fairly similar, and what you want to use there is this complex exponential function that I was talking about earlier. So yeah, so if you're looking at e to the z, where z is a complex number, this isn't some notion of like multiplying e z times together. It's sort of pretty far removed from that. But it does line up with the real exponential function in the sense that you use the same power series to define it. So, right, when z is a real number here, this is exactly the Taylor series for the function e to the z. And so this sort of thing does make sense if z is a complex number, right? You can multiply complex numbers together and you can add them together. So doing something like z to the n over n factorial and doing a sum of that is perfectly fine to do over the complex numbers, at least for a finite sum. And then it's fine. You can do limits in the complex numbers too, and this series will converge for the same reason it converges when z is a real number, so everything's okay. Okay, and what's even better is that this exponential property that we have over the real numbers, e to the z1 plus z2 is equal to e to the z1 times e to the z2, will actually still hold even if you're just working with this power series definition for complex numbers. Okay, so that's nice. In particular, if you write your complex number in terms of its real and imaginary parts, say lambda plus I mu, like we were earlier, then you have this formula that e to the lambda plus I mu is just e to the lambda times e to the I mu. And now right here, this is just a real exponential function now. So now all that's left is to deal with this e to the I mu function. We want to relate that back to something that we can understand. And the way to do that is with this power series calculation. So we plug in I mu back into this power series that we started with. And now we have this I mu to the n going on here. And so to analyze what's going on with that, we want to see what's going on with I to the n. And so the answer is, well, we know that I to the 0 is just 1. We know that I to the 1 is just I. Oh, sorry, I to the 1 is I. Yeah. I squared is minus 1, and then I cubed will then be minus 1 times I, which is minus I. And then I to the 4th, we'll be back to positive 1, right? Because it's minus I times I. So that should be equal to 1 again. All right. So, or sorry, this should be I, not 1. All right, so I to the 1 is I to the cubed is minus I. So we can split these I to the n's into even and odd powers. So the even terms are real and the odd terms are imaginary. So here are the even terms. Here are the odd terms. We can pull an I out of all of the odd terms because I to the 1 and I cubed will alternate back and forth between I and minus I. Right, the next one would be I to the 5th, which would be positive I, and then I to the 7th would be negative I, right? We'll alternate like that. Similarly, with the even powers, we have I to the 0 is 1, I squared is minus 1, I to the 4th is 1, I to the 6th is minus 1. All right, so those will alternate back and forth as well. So that's where you get these two series. So in terms of the even and odd terms, you have this -1 to the k, which is saying that you're alternating between +1 and -1 as you go between consecutive terms within one of these series. So between consecutive even numbers, the sign switches, and between consecutive odd numbers, the sign switches. Anyway, these two power series are the Taylor series for sine of mu, cosine of mu, and sine of mu, right? This even one with the mu to the 2k is cosine of mu, and this odd one with mu to the 2k plus 1 is sine of mu, and we have this I out in front because that's the one coming from the odd powers of I to the n. Okay, so this is what's called Euler's formula. We've figured out how to write e to the I mu in terms of functions we recognize, right? Here, mu is a real number, so cosine of mu and sine of mu, those make perfect sense to us. Although, if you wanted to, these power series definitions will allow you to define cosine and sine as, complex functions as well. You can define cosine of z just using this power series, and similarly with sine of z. Anyway, all right, so we figured out how to evaluate these exponential functions. So now we want to go back to our differential equation situation. So we have a complex conjugate pair of roots. R1 is lambda plus I mu, and R2 is lambda minus I mu. And so we can use that exponential property with regard to sums and Euler's formula to write out the two solutions, e to the r1t and e to the r2t, in terms of exponential functions and trig functions. Right, so first we have e to the r1t, which is e to the lambda plus I mu times t. We split that into the real and imaginary parts like on the previous slide. E to the lambda t times e to the I mu t. And now we use Euler's formula on e to the I mu t, so we can write that as cosine of mu t plus I times sine mu t. And now for the other one, e to the quantity lambda minus I mu times t, we use Euler's formula again, but here we'd have like cosine of minus mu t here, but this is a trig property that this is the same as cosine of mu t, and we can use that, sine of negative mu t is the same as negative sine of mu t. That's another trig property, so that's where this minus sign comes from. Okay, so we've written out these complex exponential functions which solve our differential equation in terms of things that we can make sense of, but we still haven't arrived at real valued solutions yet. But that's not too hard to do, right? Because we're allowed to take any linear combination of these things with complex coefficients, right? This is the superposition function that anything like c1 y1 plus c2 y2 with c1 and c2 complex numbers, that will also be a solution. So we can use that to find some real valued solutions. So just looking at these, right, if you add these two together, y1 plus y2, that will get you e to the lambda t times cosine of mu t with a factor of 2, right? The sine terms will cancel, and then you'll add together the cosine terms. You'll have 2 of them. So if you just take y1 plus y2 and then divide by 2, that's a perfectly reasonable linear combination. You'll end up with this function, e to the lambda t times cosine of mu t. So that should be a solution. Similarly, if you subtract the two, y1 minus y2, the cosine terms will cancel out, and then the sine terms will combine, and you have an extra factor of I. So you'll have 2i times e to the lambda t times sine of mu t. So if you divide by 2i, then you'll get this function, e to the lambda t times sine of mu t. So subtract and then divide by 2i, and you'll get that one. Okay, great. So these are real valued solutions. The last step is just to make sure that they're actually linearly independent, so that the Wronskian determinant is non-zero, and that will tell us that we can use them to write out the general solution of this differential equation. And it's a somewhat annoying computation, but it is true. So you have to use the product rule when taking the derivatives of both of these functions. so it's a little bit troublesome. So first, in the Wronskian, you leave the first function alone. That's this e to the lambda t times cosine of mu t. And then do the derivative of the second function. So we'll get a lambda popping out when we do the derivative of e to the lambda t. And then we get this mu popping out when we do the derivative of sine of mu t. Then there's a minus sign in the Wronskian formula. Then we take the derivative of e to the lambda t times cosine of mu t. So again, we get a lambda popping out when we do the derivative of e to the lambda t in the product rule. And then we'll get a negative mu when we do the derivative of cosine of mu t. And then the second function, e to the lambda t times sine of mu t, is left alone in that term of the Wronskian. Okay, so if you look at this, the terms with a lambda in them will actually cancel out, right? You have lambda e to the lambda t sine of mu t times e to the lambda t cosine of mu t. And then in the next one, you have lambda e to the lambda t. Then there's a sine of mu t over here, another e to the lambda t, and a cosine, right? So you'll end up with lambda e to the 2 lambda t sine of mu t times cosine of mu t appearing in both. There's a minus sign on this second one, so those cancel out. Then the other two terms will combine. And so here you have a cosine squared, and in this one you have a sine squared. And you have a factor of mu e to the lambda t times e to the lambda t appearing in both. So that's mu times e to the lambda, mu times e to the 2 lambda t times the quantity cosine squared plus sine squared. And then, of course, this is all just equal to 1. Okay, so we get mu e to the 2 lambda t. This will be non-zero as long as mu is non-zero. So the imaginary part is non-zero. And that's more or less just saying that the complex roots are actually distinct. They actually are complex numbers that are complex conjugate pair, and they're distinct. Right? If mu is 0, then you have a repeated root of r1 equal to r2 just equal to lambda, which will be the next case we're talking about. But it won't be this case of a pair of complex conjugate roots. Okay, so we're all good. Superposition principle and all that Wronskian stuff we talked about in the previous lecture tells us that we have found the general solution. This is the real value general solution, so we want C1 and C2 to be arbitrary real constants, and these other functions, e to the lambda t, cosine of mu t, and such, those will be real valued functions. All right. So let's do a quick example. So let's try to solve this initial value problem and describe this behavior of the solution as t goes to infinity. All right, so the first thing to do is find the roots of the characteristic equation. In this case, the characteristic equation is r squared plus 2r plus 4 is equal to 0. And so now we just use the quadratic formula. So minus 2 plus or minus the square root of 4 minus 16. So this 4 is 2 squared. Yeah, all right, so the square root of negative 12 is I times 2 times the square root of 3, right? It's 2I square root of 3. Because 2 squared is equal to 4, so you can bring the 4 out of the square root as a 2. In any case, that 2 will cancel with this 2 in the denominator. And you're left with minus 1 plus or minus I times the square root of 3. All right, so we have the roots. They're a complex conjugate pair, like I said, right? If you look at the quadratic formula, if you have real coefficients to start with, this will always be the case that you get a complex conjugate pair. And so now, by the work we've just done, we can write down the general solution. It'll be C1 e to the minus t times cosine of the square root of 3 times t plus C2 e to the minus t sine of the square root of 3 times t. All right, so now all that's left is to find these coefficients, C1 and C2, that solve this initial value problem. If we plug in t equals 0 into this equation for y, this sine term is just going to go to 0, right? Sine of 0 is 0. Cosine of 0 is 1, and e to the 0 is also 1. So the right-hand side just ends up becoming c1. And we have the initial condition is that y of 0 is supposed to be equal to 2. So that tells us that c1 is actually equal to 2. All right. Now we need to take the derivative, which again we have to do the product rule. It's kind of annoying. So here we've plugged in c1 is equal to 2 already when doing this derivative. And then we pick up this minus sign from taking the derivative e to the minus t. And then in the second term, we pick up a square root of 3 from taking the derivative of the cosine term. Similarly, for the other two terms, we pick up a minus sign from the e to the minus t and a square root of 3 from taking the derivative of the sine term. All right. Now we plug in t equals 0, and once again, the two sine terms will go away, so actually we only care about the other two terms. And e to the 0 and cosine of 0 are both 1 again, and so we'll end up with 3, which is our initial condition from y prime of 0, should be equal to minus 2 plus c2 times the square root of 3. And so c2 should be 5 over the square root of 3. All right, so that gives us the solution of the initial value problem. We'll have a 2 on that first term and a 5 over square root of 3 on the sine term. All right, and the behavior as t goes to infinity, these are oscillations with decaying amplitude, right? So sine and cosine will both oscillate back and forth as t goes to infinity, but this e to the minus t term will go to 0 as t goes to infinity. So we have oscillations, but the amplitude will decay to 0. And exponentials go, e to the minus t does go to 0 quite quickly, so you can see this amplitude will decay quite rapidly, in fact. All right, so this is exactly the behavior of a mass on a spring with friction, right? It'll oscillate for a little while, and then it'll settle down as friction causes it to lose all of its kinetic energy. Which makes sense because this was exactly an example, like I said, right? This is exactly that mass on a spring problem with m is equal to 1, gamma is equal to 2, and k is equal to 4, right? All three of these constants are positive, so this is a mass on a this could represent a mass on a spring with friction. Okay. So that'll do it for the complex roots case. Next, we'll move on to talking about repeated roots. All right, so when do you get a repeated root from a quadratic equation? Well, if you look at the quadratic formula, it's exactly when that term inside the square root is 0, right? The b squared minus 4ac appearing in the quadratic formula. If that is equal to 0, then you'll have a double root, right? All right, so you have a repeated root if and only if b squared minus 4ac is equal to 0. And in that case, your root that is repeated, as you can see from the quadratic formula, is minus b over 2a. Okay, so we know about one solution already, right? It's e to the rt, or in other words, e to the minus bt over 2a. So now the question is, how do we find another linearly independent solution? So another solution where the Wronskian of them will be non-zero, right? We also know that we could multiply this solution by any constant, and that would be a solution. Y is equal to 0 for all t, that will also be a solution, but neither of those will be helpful for us to write down the general solution because the Wronskian will be 0 in those cases. All right, so the strategy, all right, so I did say that c times e to the minus bt over 2a being a solution isn't helpful, but it does help inform our strategy, which is that we replace this c with with an arbitrary function v of t. And the idea is that by doing this, we're hoping to get some kind of nice cancellation in the differential equation, and that hopefully we'll end up with something that we can actually solve at that point. And the answer is yes, we will get something we can solve at that point. But the reason why you might suspect that's going to happen, right, taking derivatives of this sort of thing will involve doing the product rule. So there will always be terms where you leave this v of t constant, and we know that in the case where we were just dealing with a constant, we're going to get 0 when we plug that into the differential equation. So we're going to get some other terms involving the derivatives of v, but all the terms that just involve v itself are going to go to 0 when we plug them back into the differential equation, because we know already that a constant times e to the minus bt over 2a. All right, so at least we know like a lot of cancellation is going to happen, and so you hope that that's enough to give you something you can actually solve. All right, so this method is called reduction of order for a reason that we will see soon. And in fact, it doesn't just work in this repeated roots of a characteristic equation situation for the constant coefficient case. It actually works for any second order linear homogeneous equation as long as you know one non-trivial solution y1 of t to start with. Okay, so we'll work through the method in this general case, and then we'll go back and apply it to the repeated roots case. All right, so we assume we have some solution. Non-trivial means it's not the 0 function. It's not identically equal to 0 for all values of t. We'll write y of t is equal to v of t times y1 of t, and plug into the differential equation and hope that we get something reasonable that we can solve for v. All right. So when we take the derivatives, like I said, we'll do the product rule. And so we'll have these terms where we don't have any derivatives of v appearing, and then we have the other terms where derivatives of v will appear. Now we plug all of that into the differential equation. So this first line here is just plugging into the differential equation. Right, we used our formula for y double prime, we use our formula for y prime, and we know that y is equal to v times y1. And now we collect terms. For various derivatives of v. So there's only one term that involves a second derivative of v. That's this one. Right, that's coming from the one term in y double prime that involves v double prime. Then there will be two terms involving v prime. One of them is coming from the second derivative of y, and one of them is coming from the first derivative of y. So those are those two terms, 2 times y1 prime plus p of t times y1. Those will be the terms that are multiplied by v1 prime. And then finally, the terms where v is left alone, like I said before, that's just the original differential equation applied to a constant times y1, essentially. So we end up with exactly the original differential equation with y1 plugged into it, with a v coming along for the ride, just as if v were a constant. And so we know that this is 0. This whole thing is 0, since y1 is a solution. All right, so we're left with the other terms, the v double prime and v prime terms. And now the trick is, it's still a second order differential equation in terms of v, but because there aren't any terms involving v itself, there's only a v prime and a v double prime, it's actually a first order differential equation in terms of the derivative of v. So if we treat w equals v prime as the unknown function we're trying to solve for, then this is a first order differential equation. All right, so that's where the name reduction of order comes from. We started with a second order differential equation. We ended up with a first order differential equation. And we know how to solve some first order differential equations at least, and yes, we can solve this one. This is a linear one. It's actually linear and separable, so we definitely know how to solve it. Right, it looks a little complicated, but remember, y1 of t is supposed to be a function that we just know about, right? That's the one solution that we know about to start with. So it's not an unknown or anything. It's a known function. It's just like p of t. It's a function that we know about. Okay, so we can define this capital P of t as, all the stuff appearing in the differential equation when put in standard form. So divide everything by y1. So you have 2y1 prime plus lowercase p of t times y1 divided by y1. And then the differential equation you get is this first order linear separable differential equation for w. Y prime plus capital P of t times w. And yeah, we've solved things exactly like this several times at this point, so I won't go through it. But the solution is just an arbitrary constant times e to the negative integral of capital P of t dt. Right, separation of variables will get you this right away. Or in terms of an integrating factor, yeah, you could figure that out somewhat quickly as well. Okay. Right, so that's our solution for w, which is v prime. But we're actually interested in y, which is v times y1. So first we have to get v, and that means we know v prime as a function of t, at least in terms of integrals and such. So to undo that, we just take another integral. Yeah, I'm using the c2 as the arbitrary constant here because another arbitrary constant is about to pop out, and that's the one that I want to call c1. Okay, right, because we did another integral from go from v prime to v, so we get another arbitrary constant. And then finally, we multiply that all by y1. And so we end up with this solution, y. It'll be c2 times this expression involving two integrals. And that will be this function y2 that would appear in the general solution, right? And then we have c1, y1 as the other term appearing in the general solution, right? y1 was a solution we started with, so we know the general solution should involve some arbitrary constant c1 times y1. And something just like that popped out when we did all these integrals, so that's why I wanted to call that arbitrary constant c1. Okay, right, so there we go. So that's the method of reduction of order. You don't really have to memorize the whole method if you don't want to. You can just, it doesn't take too long to end up with this differential equation. Or you could, start with this. But memorizing this formula in terms of all these integrals and stuff is not necessarily valuable. But you just remember the way the method works is you write y is equal to v1 is equal to v times y1, and then try to solve for v from the differential equation at that point. All right, so what happens back in the original thing we were interested in, this repeated roots of the characteristic equation situation for constant coefficients. So we need to figure out what this capital P of t function is. So the formula from the previous slide was 2y1 prime plus lowercase p of t times y1 all divided by y1. So here y1 is this exponential function, e to the minus bt over 2a. For its derivative, this minus b over 2a will pop out. And p of t is not b, but it's b divided by a, because remember, this lowercase p of t came from the standard form of this second-order linear homogeneous differential equation. So we have to put our constant coefficients thing into standard form. So that involves dividing the whole thing by a. All right, so if it's in standard form, then you see the coefficient of y prime, which is lowercase of p of t, is actually b over a. All right, now we put all that into the formula. So 2 times y1 prime, which is this thing, plus p of t, which is b over a, times y1, which is the exponential function, all divided by the exponential function. But you can see these twos will cancel, and then we're just left with minus b over a times the exponential function plus b over a times the exponential function, so the whole thing's 0. All right, well, that makes that whole differential equation very simple, right? This differential equation over here will just be v double prime is equal to 0, which will immediately tell you that v prime is an arbitrary constant. Or you could start from this formula. It's c2 times e to the minus integral of capital P. We know that capital P is 0, so we're looking at e to the integral of 0. All right. Then we do another integral to undo that. That will get us, yeah, I guess this isn't exactly true, right? Yeah, I guess that's one integral of 0 dt is 0. And we already have the arbitrary constant. So, but yeah. All right, yeah, that's fine. Yeah, or you could just start with this like we did. Anyway, yeah, starting from v prime is equal to c2, we do another integral, we'll get c2 times t plus c1, and now we multiply the whole thing by y1, which was this exponential function. So we end up with c2t times e to the minus bt over 2a plus c1e to the minus bt over 2a. All right, so this t times the exponential function is our second solution. Okay, so yeah, when you have a repeated root, that's how it'll work out. The exponential e to the rt will be one solution, and then t e to the rt will be another solution. And the general solution will be arbitrary linear combinations of those two. Of course, to verify that, we want to quickly show that the Wronskian's non-zero. And we can do that with another fairly easy computation, right? We do have to use the product rule once, but it's only once as opposed to twice like on the previous Wronskian computation. Okay. So yeah, first we take the derivative of this, which is when we use the product rule. So it'll be e to the minus bt over 2a minus bt over 2a times e to the minus bt over 2a. So the first term is doing the derivative of t, the second term is doing the derivative of the exponential function. The second term in the Wronskian, then we're just doing the derivative of the original function, so then we just get the minus b over 2a popping out. And once again, we see where we get some nice cancellation here. So this time, this term and this term will cancel. All right, you have a 1 minus sign on the first term and 2 minus signs on the second term, so they cancel out. All right, so you're left with just this first term here, which would be e to the minus bt over 2a times e to the minus bt over 2a. So you're multiplying two exponential functions, so you add the exponents, so you're left with e to the minus bt over a. All right, yeah, that's an exponential function. It's never 0. We're good. We can solve any initial value problem with superpositions like this, so that's the general solution. All right, and the last thing we'll do is one quick example of this. So let's solve this initial value problem, y double prime minus 4y prime plus 4y equals 0, with initial conditions y of 0 equals 1 and y prime of 0 equals 1. All right, so again, we'll want to find the roots of the characteristic equation. Presumably, if I'm doing it as an example now, it'll be a repeated root, and yeah, that's the case, right? You can see that r squared minus 4r plus 4 is just r minus 2 quantity squared if you factor it. So we have 2 as a repeated root. So by all the work that we've done with this reduction of order method, we know that this is the general solution, c1 e to the 2t plus c2t e to the 2t. All right, and now to solve the initial value problem, we just plug in our initial conditions. Things are pretty nice again. If we just plug in t equals 0, this term will go away. So that tells, and then e to the 0 is 1, so we know that c1 is y of 0, which we know should be 1. Now we can plug that in and then take the derivative. We have to use the product rule again. So I'll end up with 2 e to the 2t plus c2 e to the 2t. So this is the term where you take the derivative of t. This is the term where you take the derivative of e to the 2t in the product rule. We plug in t equals 0 again, and once more, this term involving a t will go to 0. And so we have 1, which is y prime of 0, should be equal to 2 plus c2, right? The e to the 2t's will both be 1. So we have 2 plus c2, and so that tells us that c2 is equal to minus 1. And so finally, we just plug in those values back into the general solution. So we get y is equal to e to the 2t minus t e to the 2t. All right. I will stop there. Here are the quantum formalism links. And in the next lecture, we will talk about non-homogeneous linear second-order differential equations.